All right. So we have looked at the effects of tides when they are weak. In other words, when they only produce a small deformation of the equipotentials of an object. Now we can start thinking about what happens when they are much stronger. The ultimate strength of a tidal force comes in the case where the tidal force actually destroys the object. You know, if you've got an object with its self-gravity holding itself together, and then you've got this perturbing object coming in, and of course the gravitational pull on one side is stronger than on the other side. If that difference is stronger than the forces that hold the thing together, it'll get blown apart. It'll get broken apart. And you might have even done this comparison at some point, right? You can just take the central gravity of object M1 here and compare it to the force, to the gravitational force from object 2. I'm writing it using the language of the previous video, where we can just take that second Legendre polynomial component, just look at it along the line of centers. Actually, what you get out of doing that whole process is just this 2gm times r over d cubed, basically what we got when we just estimated the force, the differential tidal force by taking the differential, by taking the derivative of the gravitational force. But when those two things are equal, you can rearrange them to get that the ratio of m2 to m1 times the cube of the ratio of the radius to the distance, which we called q. But in this case, the q is 1/2. Before, we were looking at values of q that were very, very small compared to 1. Here, it's 1/2. 1/2 is going to be the largest value of q that we ever see here in tidal theory, because if you exceed that value, there's no object anymore to hold itself together. Now, there are some other values other than 1/2 that one can actually look at. We can actually go back to our circular restricted three-body problem because we essentially have already done this problem in a slightly different way. Think about that L1 Lagrange point in between the two bodies. That's also the place, the distance to that point is sort of also the place where the gravitational force from one and the gravitational force from the other are balancing each other. But when we did it in the circular three-body problem, we also were careful to include the centrifugal term, which changes the force balance a little bit. And if you go through the derivation that we looked at for the Hill radius, you know, from M2, the less massive body, to its first Lagrange point, we had this quantity of, I think it was q over 3 to the 1/3. Well, in the current notation, that's going to be m1 over m2 divided by 3. And when you rearrange that in a way to get something of, to get the critical value of q, you get 1/3. So it's really the same concept, but with a slightly different criterion, 1/3 versus 1/2. That's the impact of the rotating frame versus not taking into account the rotating frame in the earlier calculation. But it still gives you the same physics. The other thing that people sometimes do is to assume a value of the critical q, but then solve it for the distance d, right? If you're on some little moon or a planet and something massive is coming your way, how close does it have to get in order for the differential tidal forces to break up the thing you're standing on, M1 and R1? So you can plug in whatever value of q critical you want for that. Yeah, and the values of q critical that come out of sophisticated numerical models, there's a range because, actual objects are extended bodies, fluid, solid type bodies. And the gravitational forces depend on the internal structure, right? You can't just assume all the mass is concentrated at the center. So these critical Q values actually range between about 0.07 and 0.3, although as a standard, people often still use the 1/2 value as the traditional so-called Roche limit for the formation, for the breakup of a moon as it approaches a planet and, essentially forms rings like the rings of Saturn. But you can also get insight by this range of Q critical values. So for example, we can look at Saturn as M2, the perturbing body, Mimas, the innermost large moon of Saturn, as the body that we'd like to know whether it's going to be broken up or not. And it approaches Saturn, and we'd like to figure out what are the Q critical values. And if you plug in the range, essentially the entire range that we've talked about of 0.07 to 0.5, the corresponding critical distances correspond kind of almost serendipitously to the inner and outer radii of the rings of Saturn. This is a sketch from James Tuttle Keene, who does a lot of neat sketches on Twitter. And I added the Q critical values because he called them the fluid Roche limit and the rigid Roche limit. But yeah, now this isn't the full story for how Saturn's rings are formed. I have a link in the description for a paper that essentially addresses how are Saturn's rings formed. And it turns out it's not just Mimas or other moons that started off at Mimas's place and then got disrupted, but it's actually interactions from 6 or 7 different moons of Saturn that all sort of have to work together to produce the rings that we see. Okay. Yeah, so all of what I just said is true, but we also neglected something important. We neglected the solid nature of these planets. We assumed that when we computed equipotential surfaces that were distorted by the tidal forces, that would just be the surface of the body, right? That all of the little components, the fluid, parcels would just naturally arrange themselves along those equipotentials. For solid objects, there are competing forces, right? They don't just float freely on equipotential surfaces. There are other forces. There's tensile strength type forces. If you look really down at the molecular level, that's essentially electrostatic Coulomb forces that are holding the solid material together and giving it strength. But on a macroscopic scale, you can think of it as a strength or rigidity type parameter that has units of pressure, essentially units of force per unit area. So we can talk a little bit about several different versions of these strengths. The one that you see most often, I think, is this so-called compressive or crushing strength, right? How much is an object going to resist external forcing if you're trying to compress it or crush it, as, for example, what gravity does. You can look up the properties of different materials. Naturally occurring materials have a range of relatively low tensile strengths, and I'm just listing some human-made, human manufactured or human isolated things like pure metals and even carbon nanotubes as stronger objects. They basically use the same set of pressure units to define what we mean by how strong is a solid material. And there's one interesting little problem that you can solve, and that is, how does the tensile strength compete with gravity, and which one wins? In other words, for a very massive object, we know they're spherical. Stars, gas giant planets, even Earth mass planets tend to be spherical. And that is because gravity is much stronger than the tensile strength. And again, I'm using different terms here. Gravity is a force. Tensile strength has units of pressure. So the apples to apples comparison is going to be the hydrostatic pressure gradient that gets set up due to gravity and thus creates a high central pressure in an object. You can estimate that, of course, just by balancing the pressure gradient force and the gravitational force. I just take the actual terms, the actual magnitudes, and express them just using back of the envelope order of magnitude analysis to figure out the units. A constant density object, like something made of rock or ice, is going to have a constant density, and it's going to have this quadratic pressure drop from the center to the surface. And you can think of this mass that I introduced in the gravity as essentially just the density of the material times its volume. And we can forget about factors of, 4 pi over 3 in the spherical volume formula and just, write down that as rho r cubed and combine it together and get a nice expression for the central pressure of a solid object with a given density and a given radial size. Okay, why did I do that? Well, it's this gravitational pressure that we have to compare with the tensile strength pressure to see which one wins. If the gravitational pressure is stronger, then that means gravity is able to distort this thing into a spherical shape. If the tensile strength is stronger, then gravity is not able to do that, and the shape of the object is just whatever it happened to be as random objects collected together to form that object. Right, so you can of course take this and rearrange it to get a minimum or a critical radius, right? If the radius is bigger than this easily computable quantity for a given type of material, then it'll be spherical, gravity will win. If it's smaller, it won't be spherical. And this has been done. You can compute the critical radius for silicate rock as something between about 300 or 400 kilometers. And for ices, it's a little bit smaller. And there's this paper by Lineweaver and Norman. The title of the paper is something called the potato radius, because this critical radius basically says if you're smaller than that, you'll look like a potato. If you're larger, you'll look like a spherical planet or a moon. And you can see that it seems to work out. These images were in this 2010 paper, and I think we can do a much better job now with missions in the past 10 years. In the bottom middle there, I just added the double object that New Horizons passed by a couple years ago at a length of about 18 kilometers, certainly very non-spherical. But yeah, you can see that at around 200, 300 kilometers in radius, that's about when things start to become spherical. Okay, so that didn't have anything to do with tides, but there is a comparable strength or rigidity parameter that does have to do with tides. That's called the shear strength or shear rigidity. In other words, what is the ability of the material to resist pushing on the object in a non-compressive way, right? The compressive strength was basically what gravity would want to do to itself. What a shear does is the kind of deformations that we're talking about from the tidal forces. So you can parameterize the shear strength in terms of this so-called tidal Love number. I had to look it up. It was named after someone named Love, Augustus Love. And there are several versions of it in different subfields. But in tidal forces, you can sort of write it like this, with a order unity constant in the numerator, another order unity constant in the denominator, plus this dimensionless ratio of the shear strength to something like the central pressure of the self-gravitating body. This rho gr is really just another version of that central pressure that I wrote a couple slides ago. And it turns out that if the fluid is very weak, if the strength is low, and there's no resistance to deformation, then that thing in square brackets is negligibly small, and the Love number is 3/2, again, something of order unity. For something that's very strong, that thing in square brackets is large, so the tidal Love number is a very, very small number. And we can sort of close the loop with that. What is the tidal Love number? It's essentially a measure of how much flattening the object experiences. So the flattening ratio that we defined in the previous video is really something like the tidal Love number times the tidal Q parameter. So we were just saying that previously, if there's no solid body resistance to the motions, it's just Q by itself, or 3/2 Q. But here we can see it can be much smaller than that if the body has a strong shear strength. Right, so now, okay, why are we talking about shear strength? Well, it's nice to be able to model how little deformation there will be when there's a stronger material. But remember, that energy is still going into the object. That energy is still trying to deform it. And if it just deforms a little bit, the rest of that energy has to go somewhere else. and we see that it's a very dissipative phenomenon, right? There's a kind of a friction where the strength is battling against the desire of the force to pull it apart, and that frictional dissipation will create a source of heat inside the interior of this solid planet or moon or whatever it is, and we can estimate the strength of it. So we can go back to the definition of the shear strength. Now, it's got units of pressure, so it's a force per unit area, but strictly speaking, the shear strength is a ratio of the applied shear, the applied force per unit area, and in the denominator is the actual displacement that happens in dimensionless units to make sure the whole thing has dimensions of pressure. And I think you can see that both the numerator and the denominator have to be there for the object to have a constant shear strength, because if you double the amount of force that you're applying, you're scraping across this thing, you're doubling the amount of force that you're applying to it to squeeze it and distort it, you would have to double the amount of shear displacement because the shear strength is just a constant. But now we can solve for that force, that transverse force that stretches or deforms, and just in terms of the parameters that we just put in the definition there. And we can then integrate that force over the displacement. Remember, the force dotted into the displacement, along the displacement, and you take the integral, that's the amount of work, the amount of energy that's deposited into the object or expended by the forces to produce that motion. Now, I did this thing where I actually took the integral, this factor of r, then integrates to 1/2 r squared. But I guess maybe it would have been simple enough to just take this f and multiply it by another factor of r to get that r squared. But I did want to show you that it really was a work-like integral. So yeah, that gives us an expression for how much energy is deposited as a given displacement is induced across the body. This area that we mentioned, we should talk about. We can think about this force acting on the entire planet or moon. So then you could estimate the area just as the surface area of some cross-section of the object. So if you do that and you simplify it a bit, you basically have that the deposited energy is given by the shear strength times the size times the square of the displacement that you managed to squeeze out of this system. Now, we can turn that energy into a power, right? How much power per unit, how much energy per unit time is being pumped in, and ongoing heating is being given to the interior of this object, and we can define that energy. We can divide that energy by a time, and we can choose the orbital period of the binary as that representative time scale, because over one orbit, that's sort of the time scale over which the tidal deformation sort of sweeps through the entire planet. Right, that's the whole planet sort of corresponds to that a equals pi r squared that we input up above. So that sort of gives us a first attempt at writing the tidal power, the tidal heating rate in energy per unit time, power or watts, and we can write that out. I've seen in some textbooks where the actual shear strength is replaced by a scaling factor times the central pressure, so that you can end up writing the scaling of the tidal heating rate as some combination of parameters of m2, the perturbing body, r0, the size of the body you're sitting on, the distance to the 6th power, and this periodicity time scale. But we could actually go back to the previous expression and just write it in terms of the shear strength and the displacement, which you can compute. And we can apply it to Io, Jupiter's innermost moon, that has huge volcanoes on it. And it's in an elliptical orbit, so its tidal deformation changes over the orbit. and it does have large tidal forcing on it. If you plug in the numbers for Io, you get a bulge height of only 1/1000th of the radius, of Io, but that's still kind of large. It's still kilometers in size if Io is hundreds or thousands of kilometers in size. And thus the derived energy dissipation rate is 10 to the 25 ergs per second. Apologies for the CGS units. That's about 10 to the 18 watts, an exawatt of power. I think that's about the same, or maybe it's just a few times larger than the amount of energy that the Earth actually intercepts of solar energy from the sun, integrated across the entire Earth as a target. It's still small compared to, say, the luminosity, which is also a power unit, which is why I used L, of the sun. But again, Io is 10 to the minus 8 times the mass of the sun, so it's still kind of comparable to it's almost like a small star generating energy due to this input of energy from the tidal forces. Here's the problem. We do not observe the tidal heating rate of Io to be that large. We observe it to be about 1/10,000th of that, only 10 to the 21 ergs per second. So there was a problem with our derivation. And what's really happening is that all of this work that's being done by the tides, not all of that work goes into heating up the moon. And in fact, on one of the first slides of tides in the previous video, we talked about all the other ways that tides can actually affect a system. Tidal work can go into changing the angular momentum of the planet or the orbit, circularizing or synchronizing the orbit. And it's really only the leftover energy that goes into the tidal heating. There is a way of estimating that leftover bit, though, because that comes from the ellipticity of the orbit, the fact that it's not a circular orbit. The fact that in one elliptical orbit, Io gets closer to Jupiter, further away, closer and further away. The magnitude of the deformation changes once per orbit, and that change in magnitude is actually the component that turns out to be very easily extractable as heat. So if you have an orbit with eccentricity E, the amount of mean average over the orbit displacement that you need to input into these equations isn't just the tidal bulge divided by the size of the moon, but it's the eccentricity times the tidal bulge over the size of the moon. Yeah, it's a smaller factor, and for Io down here, you see the eccentricity is 0.0043. So it is it's just a small fraction of the total tidal bulge that gets extracted by heat, maybe because it's changing once per orbit and actually changing the shape of the moon rather than just reorienting the bulge is a much more frictional dissipative thing, and it's more likely to go into heating. So we have to take our earlier estimate and multiply it not by E but by E squared, but because the original expression for the tidal energy dissipation had a delta R squared in it, and when you do that, you get something a little bit less, but much closer to the observed value of 10 to the 21 ergs per second. Okay. Hope that makes sense. So yeah, I guess that takes us to the end of our 2-body and 3-body classical dynamics, and we will soon move on to much larger numbers of bodies interacting with one another.